Sorry, I need to look at the
camera. Thank you very much. Good morning, everybody. It's a pleasure to give this presentation for you. I'm very sorry that I couldn't come to London, but let's make the best of it as it is right now. So I'm talking about model-driven engineering and industry. And I think we all have made the experience that the relationship could be better than it is. But I would like to point out what are the, let's say, the points where improvement is still needed, and what are the root causes that model-driven engineering does not have the success story in industry that we would like it to have. And I point out how this could improve in the next couple of years even. So just a second. All this work I'm referring to today has been made with many others. So this is not an isolated effort, but I have collaborated over the years with very many other people. And I'm grateful that they gave me input to some parts of the things I'm presenting today. Let me just say a few words about myself at the university, my university research and our company. My research focus has always been on verification and validation of cyber-physical systems or safety-critical control systems. In recent years, the new focus of autonomous cyber-physical systems like autonomous road vehicles and autonomous trains and so on has slightly changed the research direction, but it is still the basic focus, safety criticality in cyber-physical systems, but with the new challenges that come with autonomous systems. And another main focus of my research is model-based testing as part of the model-driven engineering approach. And I'm working with formal methods. I've tried out lots of things. This is just name dropping here under this experience bullet. This is just to tell you, to make clear that I have some experience with modeling formalisms of very different kinds. And so perhaps it is sufficiently trustworthy what I will be talking about. Okay. Our company has been founded in 1998. It's a spin-off of the University of Bremen. And the business foci are, of course, verification and validation services for safety critical systems. But in that field, we also provide automation tools. Our flagship tool, that's the RT Tester model-based testing tool. It allows to do functional testing and has some support for worst-case execution time testing. We have other tools that are very specialized for the avionic domain, like source code to object code traceability analyzers and data and control coupling analyzers. And we have hardware in the loop test benches where our tests can be executed in hard real time. Our customers come from the railway, avionics, and automotive domain. So with model-based testing, of course, modeling formalisms are extremely important for us. And currently, we use a subset of SysML 1.6 to model the expected behavior of an embedded hardware software system. And then we have a model-based test generator that works on the basis of an SMT solver. And the SysML state machines and actions are transformed internally into a transition relation, and this transition relation is then evaluated by an SMT solver that creates concrete test data to reach a certain test objective. What our customers like about that is that they don't only get test cases, but they get compilable and executable test procedures from that approach, because we have a code generation backend here. And since SysML allows us to associate requirements with model elements, everybody knows that the satisfy relationship between states or interfaces or activities or such things and requirements, we can really do requirements-driven test case generation in an automated way. So we analyze which model elements are linked to these requirements. Internally, this is translated into LTL formulas. These are translated into first order and then thrown at the SMT solver. And then the SMT solver comes up with test cases that are suitable to cover certain requirements. So this sounds all very well, and you can imagine a lot of effort went into that tool. I think by now it's at least 100 person years. It works very nicely, but our customers are not so happy with modeling. So quite often we provide these models with our trained personnel for our customers as a service. But that our customers really apply these model-based approaches, for example, with SysML 1.6, and write their own test or development models. This is not so often the case, and often the models are not sufficiently detailed to generate code from that. And so it's not as successful as we would like it to be. And here's just one photograph. These are the test benches that we are producing, and then the automatically or handwritten program procedures are fed into the test bench, and then in hard real time, the system under test is it gets input data, and we observe while the system under test is running whether the outputs conform to the expected behavior according to the model. So, since I think that the success of model-driven engineering is not yet as high as it could be, I structure this talk into 3 parts. So I will say a few critical words why I think that the current modeling formalisms are not so well accepted as they could be. And here I'm talking about model formalisms, both invented and implemented in industry and in the academia. In the second part, I will give you a list what I think are the ingredients of a successful modeling formalism. And in the last part, I will advertise I'm convinced that the new release of SysML, this version 2, which is currently prepared for standardization in the OMG, that this is a good approach. And if you don't believe me, just consider I did not invent SysML v2. I just read about that, and then I've studied that closely, and now I think it's a good thing. So if a research community member advertises a modeling language that he or she has not invented, it must be really good, because otherwise we would only criticize it. And so perhaps I can convince you that SysML v2 has some interesting aspects that deserve some attention. So let's come to the critical part. Why, from my perspective, why is it that current modeling formalisms like UML, SysML, everything that is really supported by commercial tools, that this has not been received in the industrial community and also not in the research communities in such a favorable way as we would wish it to be? So the first thing is, I am convinced that modeling formalisms and tools should always be compared to programming languages and tools with respect to the things that we can do with them today and with respect to the end user experience of the modeler or the programmer. And my experience says, and that of our customers says, that the modeling tools that we have available today really cannot compete with the programming IDEs. In the last 20 years, the integrated development environments for code development, they have become so powerful, and their usability has become so really so good that it is really fun working with these tools. I don't know whether you agree with me. We can talk about that in the discussion. But really, when I have a programming task and I know I will now use my Xcode environment for C++ programming or IntelliJ IDEA for Java programming, then I'm looking forward to that working day. Because from my perspective, it is extremely nice to work with them.
Yeah, show that to Jonas.
Is something wrong?
Fine. There was somebody who was accidentally unmuted.
Okay. If I'm able to provoke you, that would also be a main objective of this talk. And so you see, with these programming IDEs, you can expect on-the-fly syntax checking. You have effective lookup functions for the types and operations that you have in your source code. You have powerful static analyzers and so on. And all of this is missing in our standard commercial modeling tools, at least those that I know. If you know a tool that you think is perfect for standard SysML or so, please tell me afterwards. But from my experience with these 6 or 7 tools I've worked with, this is not acceptable. And the degree of semantic analysis that I can do with IDEs is far beyond that what I can do with modeling tools. And so this is just an example with my Xcode programming environment. Here I have a fairly complex C++ function, and the Xcode static analyzer tells me, oh, look, here a division by 0 could happen. And this was actually true. This was a real bug, and it only occurred in very rare situations, but it could have occurred. And this power of semantic analysis is missing in most modeling tools. Now, another problem is that in the modeling tools, you have to decide about your action and expression language, like guard conditions and state machines and entry actions and all that stuff. And whereas the UML at a very late point in time had introduced this action language for foundational UML, I'm sure you have heard about that. This has led to the fact that nobody really knows what type of action language to use with UML. Sometimes they just insert code, but the binding between Java or C++ code and the modeling elements like classes or blocks in SysML and so on, the binding is complicated, and this is not really as elegant as it could be. And the available action languages, as this ELF, are far more restrictive than the programming languages like Java and C++. And so we have the problem that expert programmers who are used to writing code in Java or C++ or C# or something like that, all of a sudden they are forced to use an action language which is either undefined or it is far more restrictive. And I think this is not acceptable. And it's not so absolutely trivial to say, oh, then we just use C++ as the action language, because C++ allows you to do pointer arithmetic, and then you need something like a memory model. And with standard UML, SysMLU, it is very cumbersome to set up a memory model that fits to the things that your C++ programmed actions do. So that doesn't fit together. And all this reusable, these reusable classes that you have in Java and C++, they are never provided by the current modeling formalisms. Also in a simple UML action, you would like a list management package or something like that. And that's not completely trivial to use and then to map on your programming language. So the next problem that doesn't have anything to do with programming languages and IDEs is that this focus on graphical syntax was highly overrated in the early years. It started already in the 1980s when Tom DeMarco told us about structured analysis. And I remember I worked with Philips at that time, and Hewlett-Packard sold structured analysis tools, and they had leaflets promising that the productivity would be increased by a factor of 20. And then we tried to measure that in our development team, and the productivity was increased by a factor of, let's say, 1.5. And this idea that graphics is very valuable, this was highly overrated. And the problems or the reasons for that are, one thing, if you are a system design expert, then you have this structure that you wish to express already in your head, but then drawing this structure is much more tedious than expressing the desired structure in a textual way. And this can get very unnerving, especially with tools that don't give you the perfect graphical development context. And up to now, I never found a tool that is really fully satisfactory on the graphical side. And also, graphical representations, even if your tool support would be perfect for them, they are inadequate for describing very large numbers of interacting components. In the CSP process algebra, you can have parameterized concurrent processes, and your parameter can go from 1 to 2000. But of course, you can't draw 1,000 components. And of course, I know you can do something with multiplicities and all such things, but this is still not as perfect as in a textual representation. Also, this problem of dynamic component creation and deletion in varying configurations, like a robot entering a configuration of other collaborating robots. This is very hard to represent in a graphical way. And up to now, I have not seen satisfactory solutions for that. If you think you have a perfect solution for these graphical aspects, please tell me. I would be very interested in that. But I think it is extremely hard. Another thing would be mobile processes that are attaching their communication channels to different communication partners. That's also a thing that is very hard to represent in a graphical way. Up to now, I just talked about UML and SysML. Let's go to these things that the formal methods communities have presented during the last decades, for example, process algebras and B and Z and so on. There we also have the problem that just formal modeling without a code generator or without sufficient return of investment is not worth the effort. We have talked to many users of formal methods and semi-formal modeling approaches in industry. And they really say, if you can't execute what you are modeling, it's not worth anything. And of course, we know that tools like IBM Rational Rhapsody, they provide simulation code, and this is a good thing. But we would need a whole bunch of tool components to get a satisfactory return of investment for the effort that we put into modeling. Modeling is not easy. It's definitely harder than programming. You see that when you observe programmers who are quite good in Python hacking, and then they produce models that are really terrible to analyze. We need more return of investment for the effort that is put into modeling. And so what we want is on-the-fly syntax checks, static analyzers, all sorts of verification support from testing to theorem proving and requirements tracing, and of course simulation code so that you can run your model here simulation. And specifically the formal methods communities, they came up with very interesting approaches. You remember Z, CSP, the B method and its variants. They are all very interesting. But I think that their success was not as big as people hoped. The reason for that was that we really have insufficient support for object orientation, because the semantics is quite hard to express for dynamically for objects that are dynamically created and deleted and so on. And this is really, let's say, a barrier that keeps these formal modeling formalisms from being widely used in industry. Because I think it's quite accepted today that increasingly complex systems require object-oriented approaches to cope with the size and the complexity. And if your formalism like B or CSP is not really object-oriented, but you have somehow to use workarounds to get some concepts of OO into these formalisms, then this will not be satisfactory. And this object orientation becomes even more important when you talk about modeling collaborative autonomous systems today. They require changing configurations, dynamic reallocation of channels, and even for fault-tolerant systems, reallocation of tasks. And all that stuff somehow needs object-oriented concepts. And of course, the skilled programmers find them in C, C++, and so on and so on, in C++ and C# and so on. And so it does not seem to be acceptable to use a formal modeling language that does not provide these mechanisms, because people are so used to that. Another problem from the formal methods communities is that somehow this focus on mathematical syntax diverged from the development of programming syntax. So I just give you an example of a very ancient mathematical modeling formalism, this Z formalism. I think hardly anybody uses that today, but it shows the difference so nicely. When Z was invented, that was in the 70s and 80s of the last centuries, then it was seen as a big advantage that data types of variables could be mathematical data types. So this is the power set of another set. This is a partial function, and that's the domain of a function, and so on. And of course, when you compare this abstraction to assembler programming or C programming, then this is an advantage to have these data types. But of course, today, all that stuff is available in the modern programming languages. But unfortunately, the programming language designers had another approach to syntactic representation. So no C++ or Java or Python designer ever thought of introducing data types by means of mathematical functions also. The syntax is always like as you are used from programming languages. And so this is the equivalent representation of this Z schema in Java. And you have exactly the same things. So your set known is here something, but of course, it doesn't look mathematical. Here, it looks like object-oriented programming language. And I think this is an important psychological observation. The formal methods community always has worked with mathematical syntax in some way, whereas the programming communities produced things with the same expressiveness, but with a completely different syntax. And the programming community has won, as from my perspective. And so this is not of interest anymore. Today we express things like this, and therefore many of these mathematically based formalisms like B or process algebras and so on, they are not so relevant in the programming communities or in the software development communities anymore. Okay, this just shows that you can express operations in just the same way, but it doesn't look mathematical. Okay, let's skip that. Another thing that went wrong in the formal methods modeling communities is that they had some essential mechanisms that came up in all their formalisms again and again, but they are not really reflected well in the real world. For example, nearly all the process algebras rely on synchronous unbuffered communication. And this has, of course, its advantages for verification. But if you are writing embedded systems code with shared variable communication, then of course this unbuffered communication doesn't exist. The same thing is if you do message queue handling with like Linux message queues or something, then of course they are buffered. And these formal concepts of synchronous unbuffered communication, they don't occur often enough in reality to be fully appreciated, though of course they simplify verification. Another thing is that compositionality plays such an important role in the formal, many of the formal modeling languages, but this compositionality doesn't occur that often in practice because it's often ruined by the use of shared variables, and then you need semaphores and so on. So the advantages for verification with process algebras and similar things, they don't outweigh the problems that these assumptions don't really occur often enough in practice. And so this is my overview. these are my personal impressions from our customers and from what I'm talking to my students, why currently neither the industrially oriented modeling formalisms nor the modeling formalisms of the formal methods community are as successful as they should be. So what do we need for a successful modeling formalism? And I think 4 aspects have to be analyzed and attended to with equal diligence. Namely, of course, you need an interesting language design of a powerful language. We go into that in a second, but this is not enough. If the language doesn't come with sufficient tool support, and this means much more than just checking the syntax of the language, then it just won't be used. All my C++, C#, Java, and Python programs, they can be regarded as specification models on a slightly more concrete level than UML, SysML, but I can directly execute that. And if I don't have sufficient support on my modeling language, then it won't be accepted. The other thing is we need to consider business models, because in the past, the business models for selling modeling support tools have sometimes prevented modeling approaches from becoming successful. Quite simple, a tool vendor is not so interested in having new language releases every 2 weeks, because this means that they have to invest into tool extensions to cover new syntax and semantics and so on. In contrast to that, in academia, you have to invent something new all the time so that you can write a paper about that, and then you can get your PhD. And there you are interested in adding something to an existing formalism as often as possible, so to say. And these interests clash. And somehow this has to be sufficiently organized so that the end user of a modeling language always find the proper tool support and are neither hindered by insufficient tool support nor by too many changes in the modeling language. And finally, of course you need a supporting community of sufficient size, because if you just invent a new modeling formalism in your PhD work, you won't have a sufficient community to get a breakthrough for that. And this has to be considered as well. In Java, in C, and C++, and all these programming languages, you have thousands of people contributing to answering questions why this and that doesn't work in the programming language. And if you don't have such a community with your modeling formalism, then you are stuck, and this can't become a success. I would like to point out from today's perspective, what are the most important new success factors for a modeling language? One thing is today's systems are no longer static. We always talk about dynamically changing configurations of collaborating systems, like collaborating robots, or on a larger scale, collaborating systems of systems, where European railway lines collaborate so that trains can cross the boundaries and still fulfill the specifications for safe railway operation in a different country. We always have changing configurations. And so this is one of the important things that need to be nicely supported in a modeling formalism. A different aspect is that the growing complexity of application systems requires that somehow libraries of scenario specifications are supported, instead of requiring that your whole control system should be represented by one monolithic model. And this was first detected in the autonomous systems communities, where they said, for example, an autonomous road vehicle is too complex to be specified in one model. Instead, we need different scenarios. How will my car behave when driving through a tunnel? How will my car behave when driving on a 4-lane motorway? And so on and so on. And of course, there you need support for creating small parameterized models, and where you can specify how different scenarios are linked to each other. And this becomes more and more important. Recently, I had a discussion with engineers from Siemens who had developed a completely new interlocking technology where the interlocking logic could be executed in cloud server farms. A very, very interesting and I think a very successful idea. And the Siemens engineers told me, though this doesn't have anything to do with autonomous systems or artificial intelligence or something like that, we are not able to give one specification model how the system in the cloud should behave. And this library support is extremely important. And of course, I realize that also in former times, we had different functions of a very large system like an aircraft described in different models. But there, these different functions were completely partitioned. So they had very well-defined interfaces. And so it was very easy to set up a collection of models because there were just the interface definitions in between and no other relationships. With these scenario libraries, it's more complicated because one scenario may have relationships or even maybe interacting to another scenario. And so this is a thing of the future that can't be avoided with the increasing complexity of cyber-physical systems today. Another challenge are multi-agent systems. If you think of BDI agents, belief, desire, intention agents, there you have the possibility that during collaboration, even plans can be modified and exchanged between agents. So they can collaborate, and in the first step of the collaboration, they can create new plans how to reach a certain mission goal. And this corresponds to changing the behavior at runtime. And this is quite complex to express. How would you specify that the limits or the constraints within plans are allowed to change at runtime? And I'm not saying that this is relevant for everybody, but with autonomous systems, if you have collaborating drones and robots, this will become a thing of the future. And this is definitely not sufficiently addressed in today's modeling systems. Then another thing is requirements should be first-class citizens of the modeling language. We have that since SysML, so this is not a problem. But you should also be able to formalize textual requirements to a certain extent, so that requirements tracing and the generation of verification conditions become easier. And this plays an important role for automated test case generation and helps extremely well because if you do proper fine-grained requirement specification, all the test cases can be automatically generated from a model, and that's a huge return of investment, that helps extremely well to get complete requirements coverage in your verification suite. Then we need stochastic modeling. I don't go into that. For software projects that are implemented in C, C++, or assembler, we need memory models so that you can explain in your model what is the semantics of some pointer arithmetic that is performed. So these are quite a few challenging features. And this list just comes from the experience with our customers and with my students and with the research I have. And I think these are important to be at least partially addressed in a successful modeling language. With respect to tools, of course, we want model editors that allow you to switch between graphical and textual modes. The experts will prefer textual mode, but for beginners, the graphical mode is very nice because then some syntax errors can't be made from because the graphical editor can help you with that. Then we need static analyzers and code generators for simulation. And my impression is, I'm convinced that these features should actually be available with every modeling tool from the start. I think the problem with these UML, SysML tools was that some of them were quite expensive, but they just came with modeling support and a very moderate support of static semantics checking. That is not enough as a return of investment. If I'm coping with a new tool and I'm investing into hours of learning that, I want more than just a syntax check from my tool. I always want simulation code so that I can execute that. And then additional features that are not mandatory for everybody would be more verification support, like model checkers, theorem provers, automated test generations, the possibility to integrate C, C++ or Java, C# as an action language, and then optimized code generators for specific target platforms. Now let's think about the business model. What's important for the business model? The first thing that is not so hard to realize, the modeling language should be an open access standard. This has already been achieved with UML and SysML 1 point something. All the language specifications are available with the OMG. And somehow, of course, language changes have to be controlled. And I think for other reasons that come in the next lines here, you need some kind of support foundation for a successful modeling language. Like just as you have the Eclipse Foundation for supporting this IDE and how it grows over the decades, you need a modeling support foundation for the language. And this foundation would be responsible for accepting or rejecting requests for change of the language and other things that come now. The basic tool support that I had sketched on the previous slides should be open source and should come for free and should be provided by the Modeling Language Foundation and by the academic communities. Definitely the academic communities are insufficient for providing such a basic tool support because they can't guarantee continued support. But such a foundation, as we have seen with Eclipse, persists over the years, and they can guarantee that this tool support will remain available. But my impression is that it was not a good idea in the past that for this basic tool support, you should already pay. And my impression about a successful commercial model would be that the tool vendors only make profit from the advanced tool support, like code generators for specific automotive platforms and such things. And of course, this is just a suggestion, but in the past, the problem that modeling tools were quite expensive and just helped you to input your UML model and do some very basic syntax checks. This was one of the root causes that UML SysML did not become as successful as they could be. And so I think there are also enough business community opportunities with this advanced tool support. And I think it is very crucial that the basic support should come for free and already contain simulation code generation. Then testing, teaching how to use the modeling formalism and what are the best practices that would typically be done by members of the language foundation and by the tool vendors. And the community, then you need community support that could also be organized via this language foundation. And of course, this is all not technical, but from my experience, this is just as important as inventing a good modeling language, that you have these business models available. Let me say a few words why I think that SysML version 2 is a promising candidate for that. You remember this is currently being specified and will be standardized by the OMG, I think, in the next year or by the next year. And it is still a wide spectrum language. This is what all of our customers want. They never want small, well-defined languages. That they want wide spectrum with very many syntactical constructs. But these wide spectrum language has been achieved now by means of a fairly smallish, let's say, language core, and the wide spectrum properties were achieved by means of libraries. So they have a very interesting language extension structure, which is definitely simpler than the UML profile mechanism. And SysML v2 is now no longer a variant of UML or a specialization of UML, but it has its own semantics and its own libraries providing this wide spectrum syntactic language support. From the start, a textual and a graphical language have been designed in parallel. So everything can be modeled in a purely textual way, but the typical diagrams as you are used from the old SysML and UML can be modeled in a graphical way as well. This is what I just said. And the semantics is simpler, which I will show on the next slides why this is the case. And they already have a fairly large research support community. There are about 160 persons contributing to this SysML v2 definition. Now, why is the semantics quite attractive? The mathematical semantics is given to a very slim core syntax of the language. And the rest is then defined via libraries with meta modeling elements and complex SysML v2 specifications can be translated step by step into the core syntax. And then the core semantics can be derived in a mathematical way from this core representation. I think this is a good approach. It also has its drawbacks, but it is a very good idea that the mathematical semantics is associated with a very small core, which can be where it is not too hard to understand this. These are just examples how you can specify in a graphical way and textual way. And let me just summarize some of these challenging features that a language should have, how this is reflected in the UML, in the SysML v2. The modeling of dynamically changing configurations. This is very nicely reflected by a concept called performances in SysML. And these are something like containers for concurrent interacting subcomponents. And if you can't give monolithic specifications to the full behavior of these subcomponents, you can derive their evolution over time by means of snapshots and time slices and other things, so that even incomplete scenario specifications can be done very nicely with these concepts. And the scenario specification is further supported by the usual inheritance concept, which we know from UML, but by a quite powerful redefinition concept for features. You can do subsetting of features, and there's an interesting possibility for parameterization. And you have scenario-specific language extensions, or you can make them yourself, because it is quite easy to extend the language. No ready solution for multi-agent systems yet, but I think it can be done through language extensions. Requirements are very nicely formalizable in SysML v2, and they have a very powerful satisfy relationship. So this is very, very easy to do. Let's skip that. To conclude, I have criticized existing modeling formalisms both from the industry and from the formal methods communities. And I've tried to explain from my personal experience why they have not been as successful as they should have been. I have sketched some key factors for a successful new modeling formalism. And I advocate SysML v2. This seems to be the most promising candidate at the moment from my perspective. There are just some things about modeling approaches for model-based testing that might be of interest to you if you want to go deeper into these topics. But that's it, what I wanted to present today. It's of course unfortunate I couldn't see your faces, whether you started to hate me during the criticism of modeling languages, but now you can abuse me via asking fierce questions or stating that you have a completely different opinion. Thanks very much for listening. And again, I'm sorry that I couldn't attend this personally. Thank you very much.
Thank you very much.